So in this lab, we're going to consider a microphone module and how we can connect that microphone to the Arduino board. You can see here on the left side of the board, this is the microphone module that we're going to be working with. It simply has a condenser, an electret condenser microphone like the ones that we saw before. And it has, I don't know how well you can see it, it has only 3 connections. There's an out, there's a ground, and there's a VCC. So when you're looking at it from the front, that's hard to see because there's that green light there. When you're looking at it from the front, there's just an output, a ground connection, and a VCC. So we're going to make those connections to the board, but we're going to make them in such a way that we're going to minimize the noise. And I'm sharing with you here some hard-won wisdom. So please, I would encourage you to consider doing it just the way that I'm suggesting. First of all, it's probably hard for you to see, but this breadboard is being externally powered by a 5-volt power supply. You'll see these 2 wires right here. These are going to make sure that it's both the top and bottom buses. So even the power up here and the ground is up here. Those are connected as well. There are 5 connections that are made from the Arduino to the breadboard. The first of them is the easiest. That's this black wire right here. I'm going to cover that up so you can see this a little bit better. The black wire right here simply connects the ground of the breadboard to the ground of the Arduino. Then there are 3 connections that are being made between the Arduino and the microphone. Let's see, we have the 3.3 volts. This white wire, we've never used the 3.3 volt supply before, but it turns out that it is a much higher quality signal, a much higher quality voltage source that offers almost no noise, or very, very low noise. So the white connection is being made between the 3.3 volts and the power of the microphone. Then the yellow connection is offering a separate second ground connection. This one directly to the ground connection of the microcontroller. So I'm not simply connecting the microcontroller's ground to the breadboard ground. That actually caused me a lot of trouble, so I would encourage you not to do that. And then the red connection is connecting the microphone output to pin A1. So that's analog input 1, which we can then use the A to D converter, the analog read command. So what we should be able to do is with these connections in place, oh, one more connection, there's this green wire. The green wire is connecting from a pin called AREF, the analog reference voltage, and it's grabbing a copy of the 3.3 volts. I don't know how well you can see it, but the green and the white are connected together. So 3.3 volts is going from the Arduino to the microcontroller, to the microphone, and then another copy of that 3.3 volts is coming back here to AREF. That's necessary if we need to make very precise analog conversions. And in this case, we do need to make very precise analog conversions so as to minimize the noise in the system. So let's go ahead and pull up the serial plotter. And if everything goes the way that it's intended, you should be able to see my voice directly on the serial plotter. Now, the program is written in such a way that the maximum that can be read is 100. And so you can see that if I talk loudly and get close to the microphone, I can be real close to 100. But if I talk more quietly, you can see that my voice is going to record a much lower rating. I'm going to be quiet for a second so you can sort of see what's going on with just the sort of the basement level of noise in the system. Now there's an air conditioner, or in this case a heating vent in my office that's running, so that's contributing some of that noise. But another thing I want to do is just real quick here, I want to switch from powering the microphone from the nice clean 3.3 volt signal up to the 5 volt signal, up to the 5 volt power supply that we've been using for every other lab this semester. So I'm going to be quiet, I'm going to let you see the low level of noise, and then you'll see a higher level of noise. So here it goes. So notice that the noise back here is very low, but once I put the microphone, or once I put the power supply in at 5 volts, the noise increases substantially. Even when I'm quiet, it's still got a higher level of noise. So I'm going to move this back to the 3.3 volt power supply. And we're back to the nice lower level of noise. Notice if I snap my fingers, it's like an impulse function. Or if I clap, we get a nice sharp hit on the serial monitor, so you can see that there's like an impulse that's being sensed by the microphone. We're going to be able to use that in the next experiment. So what we've gained here is we have the ability to be able to visualize the audio signals that are being received by the microphone. They go into the analog input. The microcontroller, the Arduino, senses them, does a little bit of calculation on them, and then displays the result directly to the serial plotter. Now we're going to see how to use the microphone to do something a bit more useful. I'm going to institute here what's called the smart clapper, where the blue LED is going to light up every single time that I clap or snap my fingers or make any noise that's registered above a certain threshold on the microphone. And if I clap once, it'll toggle the state of the green LED. If I clap twice, it'll toggle the state of the yellow LED. If I clap 3 times, it'll toggle the state of the red LED. You can see that I've added 4 additional wires here. These are connecting the 4 LEDs to pins 9, 10, 11, and 12 on the microcontroller. So I'm going to go ahead and plug this in. And I'll see if it's still got the program loaded. And it does. So every time that I make a noise that's loud enough for the microcontroller to register it, it's going to flash the blue LED. And if it flashes the blue LED exactly once, it'll toggle the green. Flash it exactly twice, it'll toggle the yellow. Flash it 3 times, it'll toggle the red. So let's try to toggle the green. Now that may not seem like much today because you could control this so many other better ways, but trust me when I tell you that back in the 1980s that was the cutting edge of technology. And it's also kind of nice that you can see that we can begin to actuate things based on sound. And right now that sound is very binary. It's either going to be loud enough to exceed a threshold or not, but in the next few experiments we're going to see some additional things that we can do that are a bit more interesting than that. Now I want to show you how to use this this sort of LED matrix to be able to visualize some of the audio signals that we're going to receive. Before we do that, I just wanted to quickly show you that you're going to need to include some important libraries here. Now this wire.h library, and this is all in the handout, but I just wanted to show you here. You can go to include library and then go over to manage libraries and then type in the word wire. And the very first option here, you can see I've already got it installed on my computer, but you can install it if it's not there. Let me, for example, if this one's not installed, you can see that I could install it. So up here, this one's already installed. I don't have the option to install it, but you will have the option to install it. And so once you've done that, then that library will be available to you. We're also going to need to use a couple of other libraries here. We're going to need the Adafruit. That's the company that manufactures this device right here. We're going to need the Adafruit Graphic Effects library and the Adafruit LED Backpack. Now you might say, why is it called an LED Backpack? Let me pull this guy out here and show you that on the back of that display, there's a chip here. And that chip is designed to receive the serial inputs from the Arduino to remember what it was told and then to resend that signal out as necessary so that it displays it in the correct pattern. Let me just plug this back in. So we're going to need to download these 2 libraries. Now I've posted a zip file for each of these libraries, as well as another one that you're going to need for the final step, the FFT library. You're going to need these 2 libraries in zip files. So download them, put them somewhere where you know they are, and then go to Sketch and go to Include Library, and then say Add Zip Library. And then you're going to want to go to the place wherever the zip library is stored. So for me, I'll go to the desktop, I'll go to ECE 100, and then under Arduino code, and you can see here, this is where I've stored my three zip files. So you would select one of these, and then you would say Open, and then it would add that library to your instance of the Arduino software. If you get an error because it says that one of these header files is not found, then that means that you just simply haven't installed the library correctly. You can either try again or try to get some help. And so let's just see how this works once we do in fact have it correctly loaded up. I'm going to go ahead and plug this in so you can see the display. And it kind of demonstrates all the capabilities. This is called a bicolor LED matrix. Bicolor because it has both red and green LED modules built in, but if you light up both red and green at the same time, it turns out to be a sort of a yellowish orange color. So it's called bicolor, but in reality it's kind of 3 colors. And you can sort of see the red, the green, and the orange coming through here. You can see how useful it is to scroll text. You've probably seen something like this on a bank display. And it can be sideways, it can be upside down, of course it can be right side up. And however it is that you want to display it is how you can. So that's the display that we're going to be using. That's actually that one. If you go to File, Examples, and then once you've installed the library correctly, you can go down here to Adafruit Backpack Library, and then bicolor 8x8. That's the example that's being run right here. Notice that it only requires 2 additional wires. I've got the blue wire and the green wire. They're connected to the sort of 2 inputs here on the LED display, and then they're connected to pins A4 and A5. Now A4 and A5 are usually used for analog inputs, but they also serve a second purpose, and that is serial communication. So this is serially communicating all the information that it needs to display what's on this bicolor LED matrix. Serial communication means that you can only transmit 1 bit at a time, but you can transmit them really fast. You know, the video that you're watching on YouTube right now is being transmitted serially, and so it's transmitting fast enough that you can see an entire video in real time. Okay, let's look at the first use of this code. So what I'm going to do now is I'm going to upload this code to the microcontroller, and it's going to visualize the sound that's being received by the microcontroller on the LED module. So I'm going to try to speak real quietly at first. I'm not very good at speaking quietly, but you can begin to see the effect of my voice on the LED module. And you can see that sound is scrolling from left to right. And you can see that as I get louder and louder, it's going to make even more and more of the bars to light up. And the top 2 bars are in the code. They're not hardwired. They're written so that if either of the top 2 bars has to light up, they're going to light up red. And that's sort of tradition that when audio engineers would see something like this, they would say, oh, I've got the gain set too high. I need to lower the amount of amplification so that I stay down here in the green. Because if I go up into the red, it's possible that I'm going to saturate some sort of a transmitter or another amplifier later on. Now, one interesting thing to see is that I can be very quiet, and you can see that none of the LEDs light up. And then if I snap my fingers, you can see that nice impulse function that we expect to see. And if I clap my hands, you can see the same sort of an effect. And sometimes there's a little trailing bit there. You can see that this isn't always, when you clap your hands, it isn't always just 1 pixel wide. But if you clap your hands in certain ways with a very high pitch tone, you can get you can in fact get that 1 impulse function, that 1 pixel wide impulse function. It's just that you have to clap in a sort of a more particular way. So we now see that we can interface the the microphone to the microcontroller, and then use the serial communications to be able to visualize the audio signal as it's coming out onto the LED matrix. The last thing we're going to do with the microphone lab is we're going to visualize the audio signal, but no longer in the time domain. We're going to visualize it as a frequency spectrum. I'm sure that you've encountered graphic equalizers before. That's the concept of a frequency spectrum, that the lights over here on the far left will be lower frequencies, and then they'll be higher to the highest frequency over here on the right, so that the frequencies will be laid out left to right at different ranges. Now, to be able to do that, we need to do something called the Fourier Transform. If you haven't encountered Fourier Transforms yet, don't worry, you will next year. If you have, then you understand what the Fourier Transform does, is to convert something from a time-based signal to a frequency-based signal. This may not seem like it's something very important, but let me tell you that as an electrical and computer engineer, this is an extremely important idea, something that you will spend a great deal of your junior and senior year studying. So it's extremely important, and something that I wanted to make sure that you saw at least once as a freshman. one thing that I wanted to mention is that the way that we're actually performing this Fourier transform is by something called the fast Fourier transform algorithm. Again, beyond the scope of today's lesson. As a matter of fact, nearly everything that's in this last lab, in this last program, is beyond the scope of today's lesson. I'd be happy to talk to you about it, but it's pretty complicated. But the fast Fourier transform is a good thing for you to remember. It's actually a particular algorithm for calculating the discrete Fourier transform, but everyone just calls it the fast Fourier transform, so we'll call it that as well. So to be able to use this fast Fourier transform algorithm, you're going to need to include that one last library. Remember that you've already included the LED backpack and you've already included the graphics effects library. Now you need to include the fast Fourier transform library. All three of those zip files are posted for you on Blackboard. So I'm going to go ahead and plug in the LED, plug in the power to the LED module here, so that you can begin to see what I'm talking about. You can see that the frequency spectrum is, and I'm going to zoom in a little bit so you can sort of see that a little bit better. The frequency spectrum is lighting up here. And again, I've got the top two segments are lit up in red, whereas the others are lit up in green. Now, a human voice is a pretty complicated thing, and it doesn't typically exist at a single frequency. But if I try to make my voice as low as I can, which is not very low, but still you can see that I am lighting up essentially the bottom or the bottom two of the segments. And I really have a hard time lighting up just the second segment with my voice, but a much purer audio signal comes from whistling. So if I whistle, you get the idea that you can light up a single, sorry, that must have been really annoying to you, but I wanted to try to light up just those signals so that you could see each one of the bars could light up. So what you have here is a fast Fourier transform being calculated in real time and being displayed as the audio signal is received. So the audio signal is being received by the microphone. To prove that to you, I could take the signal and I could simply attach it to ground. If I attach it to ground, there's really nothing. At this point, it's really going to just show that all of the signals are lit up. But if I plug it back in, now you can see the audio signal is appearing again. So it goes from the microphone to the Arduino. The Arduino performs the fast Fourier transform. Then it sends the signal back out over these two serial lines right here, out to the LED with the backpack, and then it displays them on the bicolor matrix LED display.